Part 2. Prime mover lacking closed-loop speed control. Let me begin Part 2 with an admission of guilt. I am guilty not so much of lying to you, but rather I am guilty of withholding information from you. Understand I operate under the Kung Fu principle, in that I am always entitled to withhold one move from you, lest you at a later date come back to challenge me. Never forget this. The information I withheld from you in Part 1 is this. Even though the prime mover in Part 1 was using closed-loop speed control, it wasn't as sophisticated as I made it sound. Every time the electrical load demanded more real power, the prime mover experienced an increase in counter torque and briefly slowed down. Closed-loop speed control system recognized this fact and increased mechanical power until speed stabilized at the desired 1800 RPM. Similarly, every time the electrical load demanded less real power, the prime mover experienced a decrease in counter torque and briefly sped up. Closed-loop speed control system again recognized this fact and decreased mechanical power until speed stabilized at the desired 1800 RPM. Audibly, one can hear the generator bog down, accelerate, and eventually stabilize, as well as overspeed, decelerate, and eventually stabilize as it responded to the changing real power needs of the electrical load. The point is, even the most sophisticated closed-loop speed control system requires time to respond to changing conditions. Really, Part 2 is just Part 1 in slow motion. We're catching the generator's initial reaction to a change in real power demand before the closed-loop speed control system responds to this disturbance. As we might expect, any increase in real power demand means the generator needs to consume that much more mechanical power, and as a result, the prime mover will slow down. Decreased rotational speed should yield two noticeable effects. First, since the rotor electromagnet isn't moving past the stator poles as quickly, frequency will decrease. Second, because induction depends upon the rate of change of magnetism, voltage magnitude will also decrease. Now keep in mind this induction-related voltage decrease is on top of the load-induced voltage decrease we discussed in Part 1. This means every time the generator experiences an increase in real power demand, not only will frequency and voltage decrease because the prime mover slows down, voltage will decrease again because of load-induced effects. Let's see if this is the case. We again begin in the unloaded condition with roughly 610 milliamperes of field current establishing the desired 120 volts line to neutral, the prime mover rotating at 1800 RPM establishing the desired 60 Hz. Since this is pretty critical to our later discussion, you will note the period of each waveform at 60 Hz is roughly 16.7 milliseconds. Let's see how the system responds to an increase in real power demand when I disable the closed-loop speed control option. Our example load condition is a Y configuration of 600 ohm resistors. As soon as connection is established to this load, the prime mover immediately slows down to 1768 RPM. It's kind of hard to tell from this O-scope trace unless you look real close, but the period for each waveform is stretched out to roughly 17 milliseconds, which corresponds to a slower frequency of 58.9 Hz. Given a 60 Hz standard, this is roughly 1.8% off the mark. Now, this might not seem a big deal to you, but trust me, it is. A lot of devices use line frequency to perform critical timing and counting applications. And if frequency is off by 1.8%, everything you count or time is going to be off by 1.8%, and that is going to mess everybody up. In addition to a drop in frequency, you'll note that voltage appears to have dropped from our ideal 120 volts down to 115 volts. Faced with this less than ideal scenario, an operator has a couple options to bring the generator's output back inside the desired range. Principally increase the mechanical power of the prime mover to speed it up and adjust field current. My question to you is this: which one first, speed or field current? If you said speed, you are right. Given the rotational speed of the prime mover influences both frequency and voltage, it makes sense to resolve frequency issues first, then fine-tune voltage using field current later. This way you're not undoing previous corrections. When I up the generator's mechanical power input, speed returns to the desired 1800 RPM and frequency stabilizes at the desired 60 Hz. Given this increase in speed, voltage also increases, but stops at 117 volts, just shy of our 120 volt goal. You might initially feel stuck because any further increase in speed would increase voltage, but it would also elevate frequency beyond the desired 60 Hz. Luckily, we've got one more property we can adjust to independently increase voltage, notably field current. At an increased 656 milliamperes of field current, voltage stabilizes at the desired 120 volts. Exactly what we want, 120 volts at 60 Hz. Now, before you get the false impression that compensating for each and every load scenario is as easy as I just demonstrated, Let me assure you it is not. Sometimes this is quite frustrating, especially at the upper limits of a generator's rating. On a very basic level, you recall a generator converts mechanical power into electrical power. An attempt by an operator to increase voltage, either by increasing rotational speed or field current, also mean the load will draw slightly more current and consume more electrical power. Thus, the generator again needs to consume slightly more mechanical power. Thus, it slows down just a bit, and voltage and frequency drop, which again necessitates adjustment of the rotational speed and field current, which increases voltage, which again means the load draws slightly more current and consumes more real power, and on and on and on in this vicious recursive cycle. The fact that I hit both speed and voltage with just 2 adjustments is either a testament to my inhuman skill or luck of the dumbest variety. The world may never know. The point is sometimes that there's some overshoot and undershoot of these properties and some settling time, even for the most sophisticated of systems. Ideally, successive adjustments should be smaller and smaller in magnitude than the last, and eventually the system will stabilize. This being said, it won't be stable for long, because electrical demand is again an ever-moving target. Case in point, consider what happens when this resistive load is suddenly disconnected from the generator. In its presently compensated state, rotational speed spikes to 1837 RPM, corresponding to 61.2 Hz, and voltage jumps up to 128.6 volts. Somebody better pump the brakes on this thing before it wrecks itself. When I decrease mechanical power input, rotational speed drops to 1800 RPM, returning frequency to the desired 60 Hz. At the present level of field current excitation, voltage is still a little high at 125.2 volts. When I dial field current back to 610 milliamperes, output voltage settles back to the desired 120 volts. There you have it. Part 1 and 2. Load-induced voltage and frequency variations for isolated synchronous generators. Now, before we bring this lecture to a close, keep in mind this experiment made use of an isolated synchronous generator, i.e. one not synchronized to a larger grid. An analogy might be the one generator on some island or other remote location with no other power generation facilities. Understandably, there is a one-to-one exchange between the one generator and everything powered by that one generator. This might describe one or two situations, but more commonly, as the grid experiences increased demand, additional generators are brought onto the grid through a process known as synchronization, something we'll examine in greater detail in later lectures. As we'll learn in this upcoming lecture, once a generator is synchronized to the grid, the pooled inertia of all those generators operating in time with one another largely keeps frequency constant. This is, by the way, a simplification of what we'll soon learn is a rather complex topic. Until then, this concludes this lecture. In conclusion, we performed a practical demonstration of synchronous generators in the loaded condition. We experimentally verified load-induced voltage and frequency variations and learned those steps necessary to compensate for these load-induced changes. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest. We'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource and be sure to check out the Big Bad Tech channel for additional resources and updates.